Okay, so, yep, I think we'll start again. So, at the end of the last lecture, I kind of sprinted through a few slides, and I want to perhaps just begin this lecture by going over them at a saner pace. Also partly to remind people of some of the tools, because we're going to be using them in lecture 2. So the slides at which I sort of sprinted over were the slides that I was using to construct a feature space for kernels using the Fourier series. So this is the very first of these slides, which is where I recall the definition of the Fourier series. So most people here have encountered Fourier series before. This is very good. I just remind everyone of the notation up here, which is I'm representing a function as a sum of complex exponentials, so cosines plus some square root of -1 times sines. Okay, this is how I build up my function. And I've given an example here of a very simple function, which is just the indicator of some interval. So remember, I'm allowed to use a Fourier series because I'm on a periodic domain. So I'm on the domain minus pi pi with a periodic boundary condition, so it just loops around. Okay? So functions on this periodic domain have a Fourier series representation. I can build them up using these signs of integer multiples of some frequency. Okay? So these are the Fourier series coefficients for the top hat. And the top hat is a symmetric function, so none of these, square root of -1 times sine terms appear because they're anti-symmetric functions. All that we're left with are cosines. So what does this look like if I do a figure? So this is a figure I skimmed over very fast yesterday, so I'll explain in a bit more detail what all the parts are. So this is my top hat function, right? It's on one domain that's from minus pi to pi, periodic boundary, so this point here is the same as that point here. And so f of x is my function. What I've plotted in this square here is the Fourier basis function that I'm using, like the top one in the Fourier series that I'm using to model it, okay? So in this case, I'm modeling this entire top hat function with just one cosine. So not a very good model. And that's in blue here, okay? And over here, I'm plotting the Fourier series coefficients that I've used so far. So this component here is a DC component. That's just an offset, which pushes my cosine up. And then these two components here add together to give me the weight of my cosine. And so that tells me how big my cosine is. So I've taken this cosine, I've multiplied it by the sum of these two weights, and I've shifted it by this amount, and there it is plotted against my top hat. Okay? Now I add this basis function, but you'll notice that there's no difference in these two plots. That's because I've used 0 weight for it. I don't need it. Okay? Now I add this cosine with a little bit of negative weight, and you can see it's starting to get closer. Now I add this cosine with 0 weight, no difference. Then I add some more cosines, and the more cosines I add, the closer I get to this top hat function. Okay? So I'm building up this function here by adding a whole bunch of features which become more and more complicated. So first just a simple cosine, then a cosine with a higher frequency, then a cosine with a still higher frequency, and so on until I build up my function. So this is the short, couple of slide introduction to the Fourier series representation of a function. I can also define a Fourier series representation of a kernel, because a kernel is a function. And in particular, I care about kernels which are defined as a function of the difference of their arguments, okay? So if my kernel wasn't a function of the difference of the arguments, this whole discussion would be a little different. But in this case, I'm just saying, okay, my kernel is just a function of how the distance between the two inputs, okay? So my x here just represents now the distance of my two inputs. It's like a delta between my two things. And I can represent my kernel now also as a Fourier series. So the kernel I'm particularly interested in is the kernel that looks a little bit like the Gaussian, but for domains with a looping boundary, so a periodic domain. A Gaussian normally, it decays forever, right? And that's no use if I've only got minus pi pi to play with. So I can define something that looks a bit like a Gaussian, but that keeps looping. And so this is this thing here, which is called a Jacobi theta function. But just think of it like if my function here is much skinnier than minus pi pi, then for all intents and purposes, it looks like a Gaussian to me. And the Fourier series representation of this Gaussian-like thing is, in fact, perfectly a Gaussian. So it's a Gaussian which takes as its argument the index of my Fourier series. So are there questions about this representation? Nope. Okay, so here is my Gaussian, which I'm trying to get. This is my kernel. I'm now approximating it by just a single cosine. Here are the weights. I've also got my offset term here. That's obviously not very good, but then as I add more and more weights, I'm getting closer and closer to this Gaussian. And you can see that indeed these weights decay as a Gaussian, exactly as you would expect from the previous slide. Okay? So I'm building up my kernel using Fourier series, and I'm building up my function using Fourier series. How can I now define an RKHS using these Fourier series representations? Okay, so remember when in the previous lecture, when I defined functions in an RKHS, I had both a feature map and a representation of the functions, okay? So what was the representation of the functions? It was just like a long vector of numbers, where each of the numbers weights a particular entry in the feature map. Okay, so let me maybe just write that down one more time, if I have a white chalk, which I do. Right, so my function evaluated at x is just a sum from L equals, say, 1 to infinity of the ith component of my function representation multiplied by, say, my ith feature of x, okay? So my ith component of my function, I'm going to define using the Fourier coefficient of that function divided by the square root of the Fourier coefficient of my kernel. So that's what this entry here is, okay? And then my feature of x, my ith feature, is going to be the square root of the ith Fourier coefficient of the kernel multiplied by the corresponding complex exponential, okay? So that's my function, that's my feature map. So there are two things I need to check. First of all, if I take the dot product of my f with my feature map, do I recover the evaluation of f at x? So that's my reproducing property. And if here's my function, it's Fourier feature of f on square root of k. Here is my feature. I've taken the complex conjugate because this is a complex inner product, so the second term in that inner product I have to take the conjugate of. So I flip the sign of the imaginary component. And then indeed I get right back the Fourier series expansion of f, okay, f of x. So that worked. Does it also work that if I take the dot product between two feature maps, I get a kernel? Well, here is the first feature map, square root of k x minus square root of minus 1 lx. Here is the second one. I've taken the complex conjugate. Because I take the complex conjugate, I flip the sign of this here, okay, so this gets a positive sign. And then I just get the Fourier series expansion of my kernel evaluated at y minus x. So that worked. Okay? So everything that I need to have worked when I defined these. Okay, so this is the definition of the RKHS in terms of these features. Yeah?
This is the only kernel with this structure depending on the difference, right?
So remember that the feature map is not unique. I have used the Fourier series as a very convenient way to construct this, but I can construct any number of different feature maps which will have the same kernel.
So also only dependent on the difference of the arguments?
Right, so indeed, like if you remember the Gaussian kernel, which I constructed using the Gaussian base measure from yesterday, which had Hermite polynomials as basis functions. That's another example. So I mean, that was on RD, so this is why I got Hermite polynomials, but in a sense, right, remember the Fourier series, you're sort of integrating over a uniform measure on this minus pi domain. And so if I use some other measure that's not zero on that domain, I could get some other set of features. So yeah, so I can construct other features with the same dot product. But these are particularly convenient ones. Yeah. Okay, so the other, this is a construction and it works mathematically, but in a sense, like, what's the point? Why did I do that? So remember that one of the properties of the norm of a function in the RKHS is that it controls smoothness. So this is the important point, and this is what I get from this representation. Okay, so here is the norm. I've just taken the dot product of f with itself. That's the squared norm, in fact, okay, which is this sum here, which is the f and f hat conjugate summed divided by the Fourier series representation of k. So if my function is in the RKHS, this norm has to be finite, okay? So that means that the product of these needs to decrease faster than hat k increases, okay? So that this sum converges. More than this, if I say, like, I want to force this to be small, that means that these have to decay especially fast. So that means that the coefficients that multiply my cosines with high frequency have almost no weight. So they basically don't appear in my function. So forcing this norm to be small means forcing my function to be smooth. The next point is, so this is this point, okay? So just because a function has a Fourier series representation doesn't mean it's in the RKHS, because this is a stronger constraint, right? So remember this question that I ended the last lecture with, this top hat function. These coefficients here, this product of coefficients for the top hat function decay polynomially. The Gaussian spectrum kernel has coefficients that increase exponentially when I take their inverse. So this sum won't converge for that. So my top hat function, in a sense, has a Fourier series representation, but it is not in my RKHS because it's not smooth enough. Okay, so is that clear? Are there questions about the Fourier series construction of RKHS? Or is that okay? Yeah?
I'm a bit confused about the relationship between the norms of functions in Hilbert space and like their norms as considered as just functions on the original like set.
So here's the difference is this thing here. Like I'm basically penalizing high frequencies more than a norm which would just be the sum of the squared Fourier series coefficients, say. Yeah.
So does this is that condition like equivalent to something like saying that functions in the original space have to be smooth or have like bounded absolute norm or something?
So it's not requiring that they have bounded absolute norm, but it does require that they be smooth because it's penalizing like the non-smooth bits like quite severely, like according to one on the Fourier series coefficient of my kernel. So, you know, if I had a kernel with a slower decaying spectrum, so if I had like a Laplace kernel, it has a polynomially decaying spectrum because the spectrum decays as 1 on 1 plus L squared, I think. So that would allow for less smooth functions. I think Neil Lawrence might have hinted a bit at that as well with his Matern family of kernels. Whereas using a Gaussian type kernel, this thing here increases very fast and increases exponentially with L. And so there you're penalizing high frequencies very severely. So you've got very smooth functions coming out.
So when you say smooth,
Mm-hmm.
when you're saying smooth, as in, you don't mean like infinitely differentiable. Are you using like is there like a precise technical definition?
So if you're thinking of defining RKHS in terms of the number of derivatives that exist, you can also do that. I'm just saying smooth in the sense of not having strong components in these frequencies, but if you would like, I can also show you the derivative version, perhaps in the later times. Yeah. Okay, so this was just a quick reminder of stuff that happened yesterday. So I will now move out of evil math format and into friendly slide format. So this is my signal that things will be kinder for a while. Okay? So I've introduced RKHS just in some sort of very broad sense. Now I'm going to talk about some of the, tricks and methods that we could use to solve the difficult problems that I introduced the course from. Okay? So one of my sort of key foundational components of the work that I'll describe is a metric on distribution. So this is a distance between probabilities. And so there are a couple of ways of thinking about this. So as in my introduction to kernels, I had two ways of looking at feature spaces. One is as functions that were smooth, and one is as a space of features that somehow encode what's interesting about my variables. When I'm comparing distributions, I will think about it in exactly the same way. So I'm going to think on one hand about expected features of my distributions, which might be interesting, like mean and variance, or I'll think about a smooth function representation, which right now, probably, unless you've seen one of my earlier courses, you won't know about, but which I'll explain. Okay? Then as a special case, I'm going to show how you can detect dependence between variables, which, it should make sense to you, because if I've got features of probabilities, then I could compare the features of the joint distribution with the features of the product of the marginals, and that would be enough to distinguish dependence from independence. And that's the right intuition to have, so that's the way that I'll build that. Then I'm going to talk about a family of kernels for which these distances between feature representations of probabilities is a metric. So it is a distance which is 0 if and only if the two probabilities coincide. And again, this at least seems to be a bit mystical, because I'm saying, like, do I have features that are so rich that no matter what the difference in my distributions, I can always tell them apart? And it shouldn't be mystical, so I'm going to actually explain to you precisely why things are characteristic or not in a way that should allow you to very quickly tell whether a kernel has a characteristic property. And it really does turn out to be very simple. Then I've got a distance, but if I'm using it in hypothesis testing, I need to tell whether this distance is large enough to be significant. So, like, is my distance between distributions big enough that it's unlikely to be due to chance? Like, it's unlikely that my samples were generated by the same distribution and I just happened to be unlucky and they were a bit far apart. So that's, I'm going to talk about how to determine significance. And then probably in the next lecture, I'm going to talk about some other slightly more advanced topics. So every time I give a talk on testing, I get to the question section and somebody says, oh, but how do you choose your kernel? And I'm going to answer that question, I promise. Okay. So let's start with the notion of using features to tell apart probabilities. So who here has heard of a t-test? I hope everybody. Good. Okay, so I've got two Gaussians. They have the same variance to make life easy, but they have different means. Let's say I've got samples from each of those Gaussians. I want to tell if they're different, so I do a t-test. I say, are these means far enough apart that, these means that I've observed empirically, are they far enough apart that it's unlikely to have been due to chance? It's unlikely that this variance could explain that difference in means. Okay. So here are two Gaussians with the same mean, but they're not the same Gaussian. So my question would be now, how might I distinguish these two? Okay. So in this case, like, clearly a t-test won't be even meaningful, but you can think about the difference in some nonlinear feature of these random variables. And this nonlinear feature, in this case, is the square of the random variables. Okay? So let's look at the distribution of the square of these random variables. I've plotted these here. These are density functions corresponding to the density of the square of a Gaussian distributed random variable. So these are chi-squared densities. And you can see that the expected features are now different. So the expected x square for one is different to the expected x square for the other. And if this distance is large enough that it's unlikely to be due to chance, so you compute it empirically, you'd tell whether it's far enough apart that it's unlikely to be due to chance, then I would conclude that these are different. Okay. Here are two random variables with the same mean and the same variance, but they're not the same distribution. So I could continue for some time saying, but what if I took the fourth power of x? And then I would say, well, here are two distributions with the same kurtosis, and I could keep going. But this idea, I think, is a promising one. So, like, how might I distinguish distributions using differences of features of the random variables? And if I have a rich enough set of features, might it not be possible to distinguish any pair of distributions? Okay? So here is the kernel trick from a couple of lectures ago. So, what I have a point, I map it to some feature space. The features have to be square summable to make sure that their dot product doesn't blow up. My kernel is the unit product between features, and I can evaluate f of f at a point by taking the dot product of f and its features, okay? So this we all know. So here is something that Alex Smoller called the mean trick, which is that I represent my probability as a vector of expected features, okay? So here is my feature map. I represent my probability as a vector of expected features. Now it turns out, and I'm going to justify this in a little bit, that the dot product between these expected features is just the expected kernel. where I've taken the expectation with respect to the two random variables that I've used in defining my expected features. So mu p is my expected features for p, which is a distribution. Mu q is my expected features for q. I take the dot product of these expected features. That amounts to taking the expectation of the kernel between the random variable drawn according to p and the random variable drawn according to q. Okay? And in particular, if I represent my function here as a long vector of numbers, and I take the dot product with the expected features, then that amounts to taking my expectation of my function. So there are questions about this column here. So this is the way that I've represented my probability, as a vector of expected features. Yep, okay. So remember that these things here are indeed functions. Like every element in my RKHS is a function, and I can plot it, okay? So here is my expected feature mean, my function, which represents my probability. What does it mean to evaluate that at a point x? Okay, so here's my expected feature mean. I'm evaluating it at x, okay? That's the dot product between these expected features and the feature map at x, the standard result, okay? Now, remember that my features at x are the kernel with one of its arguments set to x. Okay, that's an equivalent representation of my feature. Now, I have defined up here that the effect of taking a dot product of any function with my expected feature map is to take the expectation of that function. That's what taking the inner product with an expected feature map does. That's from my previous slide, okay? So that means that if I take the dot product of my kernel with my expected feature map, that's just the expectation of my kernel. So this x here, this is just the point at which I'm evaluating this function, and this x here, which is done in sans serif to distinguish it from this one, is the random variable over which I'm taking this expectation. So in other words, basically, this function at x is the convolution of my kernel with my probability, the expected value of my kernel with respect to a probability. So let's plot this. Here is my probability distribution. This red function here is my mean embedding evaluated at x, okay? So basically, like, I take the expectation of my kernel with respect to this probability, and then I get a smooth function. So it's like a blurred out version of my original probability. Yep?
Why the mean embedding falls into your Hilbert space?
What, say?
Why the mean itself falls into the Hilbert space?
That is a good question. That is on this slide. So am I allowed to do this? Okay. So does there exist something which allows me to take dot products and get the expectation of a function? That is a good question, and it's like a particularly good question when things are infinitely long. So when things are not infinitely long, it's actually not a difficult question, okay? So let's say I've just got f of x. Let's just say this is like the dot product between or let's call it f1 and f2. These are two coefficients, right? And then features x and x squared. Okay? Now, if I was to take the expectation of f of x, then I would, I'd put my expectation here, right? And I could take this expectation inside here, and it would just be equal to f1, f2, sorry, that's a transpose expectation of x, expectation of x squared, okay? And this is fine. But if I've got infinitely long vectors of features, you have to be a little bit cautious about randomly switching sums and expectations. Now it turns out, so this is just the intuition, so let's look at it on this slide. What I'm sort of asking is, can I take this expectation inside this dot product? So we know that f at x is the dot product of f and the feature map at x, right? And I'm asking, like, can I take this expectation inside the dot product so I get the dot product of f and the expected feature map at x, which I've defined as mu p. So this amounts to asking about a rather technical condition to do with this random variable here, this random feature, which is whether it's something called Bochner integrable, which you can look up this to get the exact definition of. But what it amounts to checking is the expected norm of this random variable finite? So remember what we had to check with just the feature map earlier. We had to check whether the sum of the squared entries of that feature map were finite. What I need to check with a random variable, if I want to make sure that its expectation is allowed to be in the RKHS, is that its expected norm is finite. So the expectation of the sum of the squared features is finite. And this is what I'm checking here. So because the norm of the feature map is the square root of the kernel evaluated at x and x again, I'm just checking whether this expectation is bounded. If it's bounded, I'm allowed to take the expectation inside the dot product. So this is the condition I need to check to make sure that I do have this thing and that it does exist in the RKHS. So is that clear? I mean, for more details on Bochner integrability, you can check, but at least intuitively it should make sense. Like if the expected norm of this thing is finite, then you're allowed to take the expectation inside the dot product. That's not going to cause you problems. Okay, so that was like a little detour into some technical topics. Now I want to give a different intuition for telling apart probabilities. So I'm now speaking in a sort of non-mathematical scientist guise, and I'm asked, are two distributions different? And let's say that these are two distributions that give me samples on the real line, okay? And my data set that I've recorded from wherever gives me samples from one distribution here and samples from another there. And if you gave that to just somebody and said, are these two sets of points different, they would say, well, yeah, they're probably different. Now, if somebody gave me these two sets of points instead of the blue points and red points different, people would say, well, I don't see evidence of difference here. So, maybe the red points, like if I saw a lot more points, maybe there'd be a concentration of red points here and blue points there, for instance. But at least from the number of samples that I've seen, I don't have enough evidence to conclude that that's the case. Right? So now I want to capture this intuition using something that I can actually calculate. Okay? So the way that I do this is by introducing this notion of difference between probabilities. So it's called the maximum mean discrepancy, and the reason for this is that it's looking at the function from some class of functions that maximizes the difference in means, okay? So I have some set of smooth functions, which is f here, and I'm saying find me the function in that set of functions that maximizes the difference in expectation under p and the difference in expectation under q. Okay, so maximum mean discrepancy. So how does this function look for my simple case here? So I'm not telling you yet what this class of smooth functions is, though I expect you can guess, but here is a function which is smooth, which has large positive amplitude on the points from P and has large negative amplitude on the points from Q. Okay, so that pulls apart these expectations, but subject to being a smooth function. Okay, and if I computed this difference in expectations of that function, it would be large. Now, if I did the same thing for these points, this distance would not be 0, but it would be small. So I'm saying that these samples are further apart according to this measure than those samples. And smoothness matters. So if I used a function where I said it just has to be continuous, nothing else, doesn't have to be smooth, then these two samples would be equally far apart. So this function is continuous. I've said that it's also not able to go above 1 or below -1. This is just like a continuous function that pulls apart expectations. And so long as none of my points fall at the same location, any two sets of points will be equally far apart under my continuous function. So smoothness is necessary to get non-trivial results for finite samples.
We put their indicators, then this
Mm-hmm.
And is there any limit of this distance? For example, the kernel width is tending to 0 or something like this.
Right, so if my kernel width tended to 0, then I wouldn't be able to distinguish this case from this case, because my kernel would be too thin, yeah. Assuming that I'm using kernels as my function class, which I will now or shortly propose. So, here is my Gauss versus Laplace example again. So this green function is the function that maximizes the difference in expectation for Gauss and Laplace, okay? So you can see that it has large amplitude where the densities differ, and that the sign of this amplitude will depend on which is higher. So here the Laplace is higher, so it's got negative amplitude, because Laplace is on this side. And here Gauss is higher, so it's got positive amplitude, because Gauss is here, okay? So I hope everyone can see that this is a function that maximizes the discrepancy under P and Q subject to some smoothness constraints for this problem. Yep. Okay, so now what class of functions do we use? So this class of, discrepancy measures is a very old one in statistics. And so, I've already mentioned the bounded continuous functions. This is basically something, a class of functions that's very useful mathematically, but doesn't help you much in practice for the reasons that I just showed. If I use the functions of bounded variation 1, I get the Kolmogorov metric. So basically, that is a maximum distance between the cumulative distribution functions of my two variables. So anyone who's encountered Kolmogorov-Smirnov test, that's what you're using, okay? You're using a discrepancy in this class. If you use the bounded Lipschitz functions, you use the Earthmovers distance. So this is a sort of measure of distance between probabilities. It says, like, how do you move probability mass from one distribution to recover the second distribution while paying the smallest cost in terms of distance? So in computer vision, I think this is quite a popular class of distances. So we are going to use, as our function class, unit balls in reproducing kernel Hilbert spaces. So the class of RKHS that we're going to want to use are characteristic ones, which is to say that this distance here should be 0 if and only if P and Q agree. How to check that something's characteristic, I'm going to show you after a few slides, since it requires more discussion. But for the moment, all you need to remember is this unit ball in an RKHS. Okay? So are there questions about this so far? Or is that good? Yep.
So these distances that you just defined, the Kolmogorov and Earthmover, I think I missed the connection between M and D and
right. So it depends on what set of functions you use under the sup here, right? So which, these are all candidate Fs. And you can use these various candidate Fs to get a bunch of different distances.
So essentially, if set F to be the integral, then that's Kolmogorov.
So
the Kolmogorov distance, the maximum between the CDFs.
right. So if you use as your class of functions this class of functions, you get this. So we have I think a nice paper comparing these in Electronic Journal of Statistics if you want to know more. But yeah. But these are all very old distance measures. Yeah. So when I started this lecture, I said that the distance between probabilities might be seen as a distance between features. But then I switched track and said, well, actually, a good distance between probabilities is to look for a function that maximizes the expectations. So how do these two things relate? Okay, so let's have a look. Here is, I'm going to just square it, this maximum mean discrepancy. Okay, so this is, I'm looking for a function that maximizes the difference in means. Now, remember that I have said that the expectation of my function, if my function is in a reproducing kernel Hilbert space, can be written as a dot product between this, this vector of function feature weights and my expected features under P, right? So we remember this fact. So let's substitute that in. So every time I see EP of F, I substitute in the dot product between F and the expected features under P. Yep. So EP of F, dot product of F and expected features under P, EQ of F, dot product of F and expected features under Q. Okay, so that was easy. Now here, I use a rather interesting trick. In the previous slide, I mentioned that this function class was not just an RKHS, but it had the restriction that the norm should be less than or equal to 1. So this function had to be in the unit ball. And now I'm saying, what is the function in the unit ball that maximizes this dot product? So for this, I'm going to give you like a little chalk sketch. Okay. Here is a unit ball. And here, this vector here, which need not have unit links, is my vector mu p minus mu q, right? That's this vector. And now I'm finding the function with norm less than or equal to 1 that maximizes the dot product with this vector. So what's it going to be, volunteers? It's the unit vector in the same direction. So that's exactly what I've done here. I've said like the maximum function here that maximizes this dot product is just the unit vector in this direction, okay? And so the dot product of a vector with the unit vector in its direction is just the norm of that, and then I've got a squared sign here, so I put the squared in there. So is that clear, or are there questions about what I just did? Yeah?
So why exactly mu p is not dependent on f?
Why is mu?
Mu p is not dependent on f.
Right, that's right. Because remember what we said here, right? That the expected value of f is the dot product of my vector of coefficients that define f, like let's say on this example here, f1 and f2, and the expected features under p, so the expectation of x and x squared. So my expected features under p doesn't care about what f1 and f2 is. And I could change this to g1 and g2, and I could get the expectation of a function g as well. So yeah, so that's allowed. So are there any more questions about what we did here? Okay, so in a sense what we've just done is that we've taken one seemingly very tough problem, which is to find a function that maximizes the difference in expectations from some large class, and replaced it with another very tough problem, which is find the expectations of an infinitely long vector of features and then compute their difference. So it's not at least obvious here, like why anything that I've said so far is useful. So what I'm going to show now is that if I have samples from P and Q, I can compute this difference in expected features just as a function of my kernels, okay? So this is my, if I've drawn samples from P and samples from Q, this is my empirical expression for the difference in feature means. And you'll see there is no feature means in this, there's only kernels. So I'm going to show you how to prove this, but before I do, I want to just like look a bit carefully at this expression. Okay? So what do I'm assuming, just to make notation short, that I have the same number of samples from P and Q, but this reasoning would be equally true if I didn't. Okay? So what's this term here, this first term? It's an average over the similarity of every pair of samples that I've drawn from P, okay? So xi is drawn from P, xj is drawn from P, and I just take their average similarity according to the dot product of their features. What's this term here? This is the average similarity between points drawn from Q. So yi is drawn from Q, yj is drawn from Q. This is the average similarity of all pairs of points drawn from Q. And then these terms here, each of these corresponds to the average similarity of a point from P and a point from Q. Okay? And there's two of these terms here, and you know, I've got two terms here. So what do I expect? Well, if on average points from P are more similar to each other than they are to points from Q, which means P and Q are different, then this term here will be large, these terms here will be small, something large minus something small is something large, and my distance will be big. If on average points from P are as similar to each other as they are to points from Q, then P and Q are probably the same. These terms here are roughly the same size as these terms here, and the whole thing goes close to 0. So this is the intuition for this distance. So does that make sense? Okay, so now how do I compute it? Okay, so here is my difference in expected feature means squared, which I can write as a dot product, mu p minus mu q with mu p minus mu q. Then I split out the terms. So this next thing I'm going to do just on the board so I can walk through it a bit more slowly. But I also have it on the slide so that people in the other room who might not see the board can follow when I show those. Okay, so let's look just at a single term, right? Which is, let's see, a mu p inner producted with mu p. Okay? So, what's this equal to? This is the dot product of mu p with the expected feature map under p. Right? Now, remember, I'm allowed to take this expectation outside. So this is equal to a dot product of expected dot product of mu p and the feature map. And this is a random variable, just to emphasize, x, right? So I could equally write this and here is my random variable. Okay, so this random variable is drawn from P. Okay, so is everything I've done so far clear, or are there questions? Okay, so now I know that the dot product of this function here and mu p is just the expectation over this variable here, right, of this function. So now I'm going to write this, and I hope people can read it, EP. I'm going to put, so p dash, I won't write p dash. Let me see, I'm going to write p of x and then p of x dash. So these are these are the two same distributions, but I'm being very clear that x dash is a random variable with the same distribution of x, but independent of x. So it's same distribution, but independent variable. Okay, and now I've got my k of x. So this x is this one with distribution p, and x dash. Okay, which is a random variable also with distribution p, but independent of x. So is what I've done here, does this make sense? Or are there questions about it? Okay, so basically, like, I have shown that the dot product between feature map of p and feature map of p is the expectation of my kernel with two random variables distributed according to p, and one of them being an independent copy of the other. So I can give like a little example. Imagine my kernel, let's say my kernel between x and x prime was just x squared and x prime squared. Okay, so the dot product between x squared and x prime squared. Okay, now if I took the expectation of this, where x and x prime are distributed according to p, right? Then what I would get would be basically the product of the expectation of x squared and the expectation of x prime squared. So it's the product of expected features, but these two features obviously are random variables with the same distribution, but independent of each other. So that's just an example with a particular finite feature. So are there questions about this, or is that okay? Okay. So this is how I got to here. And then if I want to compute, if I have samples from P and I want to compute this expectation, this is the sum I get. Now you notice that I've required in my index of my sum that I not be equal to j. And the reason is because if I were equal to j, they would be drawn from the same distribution but not independent, right? Because it would be exactly the same variable, so they're as dependent as can be. And so I need to take away those terms with matching indices in this sum. Okay. So this is how I compute empirically my distance between P and Q. Okay, so now I said right at the start that I could get a dependence measure using the difference in feature means between the joint distribution and the product of the marginals. So I'll just do that here. So I've defined, well, I'm going to define a quantity called the Hilbert-Schmidt independence criterion. So the reason for that name, I'm going to talk about a bit more, I think, in lecture 3. But for the moment, all you need to understand is that it's the difference between the feature mean of the joint distribution and the feature mean of product of marginals. Yep?
Now MLG, is there a distribution for it so that p values can be?
Yep, I'm going to spend quite a lot of slides on showing you what that is. Yeah. Okay, so we will talk about how to construct a test from these distances later. For the moment, I'm just going to introduce the distances themselves. Yeah. So, right, so here is my measure of dependence. So I've got the features of the joint minus features of the product of the marginals. So I can write this down, but when you look at it, something might occur to you, which is that how actually do you define reasonable features for this problem, right? So imagine that I have, say, images and captions, and I need then a feature map that somehow represents the image-caption pair. And that seems to be like at least a difficult thing. Like, what's a feature that sort of encodes the information about an image and a caption together? Which is another way of saying, like, what kernel do I use for this test? Okay, so I'm going to use a particular kernel. And in, I think, a slide or two, you'll see intuitively why this kernel makes sense. But first of all, let me just define it. So let me say that I've got a kernel between a pair of images, and that's like well known how to do this. Tons of kernels on images. And let's say I've got kernels also for text. So I've got a kernel on a pair of captions. Again, a lot of kernels on text. One valid kernel between an image caption pair and a second image caption pair is the product of the kernels. Okay, so I take the product of my kernel on the pair of images with the kernel on the pair of patches. Okay, and this is a valid kernel, and it's sort of saying, well, if my images are similar and my captions are similar, then the overall similarity is big. If only one of them is similar, then the overall similarity is small, and if neither are similar, then the overall similarity is very small. So this is a valid kernel. Okay, whether it's the best kernel or not, I can't say, but it is at least a kernel that works in this context. Okay? So if I use that, then I, just as I computed before my MMD, only in terms of kernel functions, I can compute this quantity in terms of kernel functions. But here, you'll see always appearing this product of kernels on X and kernels on Y. Okay? And notice that these kernels on X and kernels on Y might be different, because here I've got a kernel on images and kernel on captions. Okay? So this quantity here is my dependence measure. So you might now think, well, okay, this I could interpret, and this I can compute, but how should I understand this as a measure of dependence? Okay, so let's see. I want to just give now an intuition for that understanding. So on the left here, I've got some pictures of animals, and on the right, I have some captions. And my task is to determine whether the images and captions are dependent. Okay? So what's a few things that we notice about this? So first of all, the captions are actually not in themselves very easy to predict from the images. So these are, I looked up pet websites, and generally, like, when people write about pets, like, they don't have this picture of a dog and say, this dog has 4 legs, it has floppy ears, it has a tail. They talk about, like, the character traits of this animal that are interesting to somebody who might want to buy it. So like, you know, they follow their noses, because this is an English hunting dog. I had to put that. And, you know, they need a lot of exercise. This one is a large animal who slings slobber, exudes a distinctive houndy odor, and so on. Pet websites are strange. Anyway, but, you know, what you can see is that, like, these things tell you something about, you know, these animals, and, like, have some sort of properties which are correlated to the pictures, but not in a simple way. And likewise with a cat, you know, it's a responsive, interactive pet that follows you around and blows in your ear. So apparently that's desirable. So, you know, and the kind of traits for a cat might be quite different to the traits that one expects from a dog. So this gives us a little bit of a clue as to how we could find the dependence between these images and captions. It's not by trying to predict the images from the captions, but to try and look at the patterns within the captions and within the images to see if there might not be some joint pattern at work. So here I've computed, or I've like sort of sketched the kind of kernel matrix that you might expect when you find good image features of these animals that are sort of animal specific, and then compute the similarities between the pairs. So these entries here, which are reasonably high, are the similarities between a pair of dogs. And then these things here are the similarity between each of these dogs and the cat. Okay? And then this L matrix here is the matrix of similarities between the captions to do with the dogs and the captions to do with cats. So here, you know, dog to dog, the similarity is high because they're both talking about like whether it follows its scent and whether it does exercise. And then dog to cat, like they have very little in common because the kind of character traits that people care about for cats are very uncorrelated with those for dogs. So what you can see here is that these matrices have a similar sort of pattern to each other. And this gives you a clue about how to determine dependence between one view of the data and a second view of the data without being able to translate between the pair. Okay? Because what I see here is that for every pair of objects in one view which are similar, the corresponding pair in the other view are also similar. And for every pair that are different, the corresponding pair in the other view are different. So imagine now I've seen like, you know, 1,000 of these things, and I've seen the matrices for all of those, and I see these patterns recurring and recurring. Then I might conclude that indeed these captions are related, are dependent on the images. So is this intuition clear? So I've never had to try and predict one from the other to determine the dependence. I've just looked at the similarity patterns within one view and compared them with the similarity patterns in the second view, and then decided whether these patterns were common to both views. So is that clear, or are there questions about this? So how would I find the similarity between these two matrices using math? Well, I could take effectively their dot product. So these H terms here are just centering terms. So they center the rows and the columns, which I need to do basically to make sure that amplitudes are not causing dependence that I need to be aware of. But effectively what this does is that it basically unrolls these K and L matrices into vectors and then takes their dot product. If the dot product is big, then probably these are dependent. If the dot product is small, then probably they're independent. So that's how you should understand this dependence measure. Yep. So I've introduced some things now. So are there questions about like the talk so far? Is that good? Okay. So now I said that I would tell you something a little more about characteristic kernels because I don't want them to be mysterious. So the first setting in which I'll describe characteristic kernels is the setting that I talked about at the very start of this lecture when I went over the Fourier series representation of the feature space. So I'm going to use this representation of the feature space to give you an idea of what a characteristic kernel should look like. And then I'm going to do a slightly more general case. Okay? So yeah, so I'm going to follow up with RD. And just to remind everyone, a characteristic kernel is a kernel for which this MMD is a metric. So it's this distance between distributions using these kernels is 0 only when the distributions agree. So this is a very powerful property that you might want in testing, and I'm going to show you that it's actually not too hard to figure out if your kernel has that property. Okay, So here's our favorite top hat function, which we've built up using cosines and sines. So these are the Fourier series coefficients of our top hat. And likewise, we've got our Fourier series representation of our kernel, which, in the case of a Jacobi theta kernel, is Gaussian distributed. So just to remind you of these facts. Okay. So if I have a distribution, I want to characterize it in the Fourier domain, so I can manipulate it in the Fourier domain. To do this, I define its Fourier transform using this notation here. So this is the conjugate of the characteristic function. So just think of this as being the Fourier transform of my P density, say. Okay? So that's, I hope people are familiar with characteristic functions, but certainly since you're familiar with Fourier series, that's all you need to know for this purpose. And remember that my mean embedding function, this is just the expectation of my kernel, so we derive this. And if I do this operation here in the Fourier domain, so if I take the expectation of my kernel, but I do that in the Fourier domain, that corresponds to taking just the product of the Fourier series coefficients of my P with the Fourier series coefficients of my K. Okay? So if I do the Fourier transform of my kernel, and I take the product of these coefficients with the Fourier coefficients of my P, then I do the inverse Fourier transform, I will get back my mean embedding. All right. And so what does the MMD look like? Well, okay, I'm just going to do exactly this operation here. I take the product of the Fourier coefficients of K with the Fourier coefficients of P. I subtract off the product of K with Fourier coefficients of Q. I take the inverse Fourier transform, so that just gives me my difference in mean embeddings. And I take the RKHS norm, which is the MMD. Okay? So this is just a very laborious and painful way of getting this original MMD that I had before. Okay, I've just done this operation here in the Fourier space and then done an inverse Fourier transform on it. Okay, so it might occur to you that you should be able to write this in a less cumbersome way if you're taking the RKHS norm of it. And that's correct, okay? So here is our expression from the previous slide. Now remember that the RKHS norm of a function is the squared modulus of the function, of the Fourier series coefficients of the function, divided by the Fourier series of the K, right? So what are the Fourier series coefficients of this function here? It's just the product of the K with the difference in Fourier series coefficients of P and Q. Then one of my K's cancel, and I just get this expression here, okay? Which is the sum of the differences of the characteristic functions of P and Q squared multiplied by this K thing, okay? So this is the math version. So let's do a version with a figure. Let's say I'm on my periodic domain with minus pi and pi, okay? And here is P. P is just completely flat. So it's a uniform distribution on the interval minus pi pi. And Q is a little sinusoid. Okay, so it's a sinusoid on this domain minus pi pi, and it's periodic boundary, so this has to match up. So what are the Fourier series coefficients? Well, the Fourier series coefficients of a completely flat function is something at zero frequency, so a DC offset. And the Fourier series coefficient of an offset plus a little cosine gives me two peaks at the frequencies of that cosine and the DC offset. Okay, so these are the characteristic functions of Q and P, respectively. So the Fourier series coefficients of Q and P. Okay, now let's take the difference. Okay, all I'm left with is these little peaks, because this bit cancels. So I have these two little peaks, and I take their square, and then I multiply them. Oops, I multiply this difference squared with K. And I take the sum, and that's my MMD. So my question now is, if I use a kernel with this Gaussian spectrum Fourier transform, will this distance be zero only when P and Q are the same? So who thinks it will be 0 only when P and Q are the same? People should raise their hands because that's the right answer. So why is this the case, okay? Let's look back here. If P and Q are different, then this difference will appear in the Fourier series coefficients, right? As it does here. Okay? So I take this vector of numbers and I multiply them entry-wise with this vector of numbers here. Okay? Now this vector of numbers here is distributed, according to a Gaussian, so it's never 0. Okay? So the product of these numbers here with these numbers here will not be 0 as long as at least some of these differences are non-zero. Okay? So if P and Q are the same, this would be completely flat. It would have no little peaks. Okay? When P and Q are different, it has peaks somewhere. And these peaks are multiplied by something which is not 0 to give this sum. So are there questions about this idea? So the thing you should notice is that as long as the Fourier transform of your kernel has no zeros, then this sum is going to be non-zero as long as P and Q are different. So if there's a difference here, it will be spotted by this kernel. So does that make sense? Yeah? So to see if it made sense, here is another kernel. This is a kernel which is like a witch's hat. And here is the Fourier series representation of that kernel. So who thinks this kernel is characteristic? Who thinks it's not? Very good. So it's 0 here. And so if my difference in P and Q occurred at this frequency, I would not see it. Okay? So this tells you that at least on this domain minus pi pi, if I give you a kernel, it's very easy to see if it's characteristic or not. I take the Fourier transform, I look for zeros, no zeros, characteristic. If there are zeros, it's not characteristic. Okay, so this idea, the same idea applies on RD with a few little subtle changes which we'll encounter shortly. Okay, so again, I've got this time my Fourier transform of my probability. This is not a sum anymore, it's just an integral. So this is just a Fourier transform of my probability. And this gives me my characteristic function. Okay? So now rather than being a discrete set of frequencies on RD, this is now a function over a smooth set of frequencies, like a continuous set of frequencies. But same idea, just for like a frequency representation of my probability. Okay? And if I have a translation invariant kernel, then Bochner's theorem tells me that this is a Fourier transform of a non-negative measure. So my Fourier transform of my kernel, which I'm going to write as d, what's this, lambda, w. Okay, this is always going to be like some function which is non-negative. So as a good example, if my kernel is Gaussian, this is Gaussian. Okay, so this thing here I'm going to denote as my Fourier transform of my kernel, and this is my Fourier transform of my probability. Okay? So just as before, like I won't go into this rather short proof, but remember, this is my maximum mean discrepancy. Remember, for the Fourier series, I could write it as the sum of the squared difference in characteristic functions multiplied by the Fourier series coefficients of my kernel. This is just the continuous version of that, this bottom equation on the slide. So I'm just taking an integral over the Fourier transform of my kernel of the difference in characteristic functions. So I replace my sum with an integral, nothing else changes. Is that clear? And you can go over the proof yourself if you like, but it's not a difficult proof. Okay, so here is P and here is Q. So P is a Gaussian, Q is a Gaussian. These are my two distributions. But Q I've perturbed with a little sinusoidal perturbation. Okay? So now the Fourier transform of P, the characteristic function of P, is also a Gaussian, because the Fourier transform of a Gaussian is a Gaussian. The Fourier transform of Q is a Gaussian with two spikes on each side. So these two spikes at these frequencies correspond to this sinusoidal perturbation. And the reason they're a little bit wide is because the sinusoidal perturbation isn't a pure sine. It has to decrease in amplitude as you increase x. And the reason is because otherwise I'd get a negative density somewhere. Okay, so rather than having a pure sinusoid, I have something a little bit broader, which is a sinusoid whose amplitude decays. And just as before, I take the difference of these two things, which is this thing here, and I multiply it by the Fourier transform of the kernel. Okay? So here is my difference in characteristic functions. Here is my Fourier transform of the kernel. Let's say I use a Gaussian kernel. So who thinks that this is characteristic? Hopefully everyone, because it's exactly the same as the Fourier series example. Okay? Here is a kernel whose Fourier transform is a top hat. Now, evidently, this is not characteristic, right? Because the product of this and that is 0. So here is the tricky thing. Before, we had this witch's hat kernel. And the witch's hat kernel had zeros in the Fourier series coefficients. And I was allowed to make my difference between P and Q exactly at those zeros and see that I couldn't tell them apart. Now I'm in RD. Now, you'll notice that when I take a perturbed version of P to get Q, these sinusoids are not pure sinusoids. So they're not located exactly at one frequency, but they're sort of spread around it. Okay? So you'll notice here that this product isn't 0. So I can witness the difference between P and Q using this kernel. So now my question would be, can I construct P and Q whose Fourier transforms differ only on a countable set? So only at the places where this Fourier transform of my kernel is 0. And it turns out that's impossible. So basically, my witch's hat kernel was not characteristic on my periodic domain, but it is characteristic on RD. Okay? So a way to understand this is because the characteristic functions of probabilities are uniformly continuous. So they're continuous functions. So basically, they're not allowed to have discontinuities only at single points. So if I take the difference between characteristic function of P and Q, it can't only spike at this point and then go to 0 and spike at this point and then go to 0, because phi P and phi Q are continuous functions. So if they differ, they have to differ on an interval. Mm-hmm.
So if you just add cosine or sine,
Mm-hmm.
just Dirac functions in the Fourier,
That's right.
then they go negative, right? So
That's
if you
right.
add DC, and that DC is going to show up there. Right?
Well, if you add a DC on all of the reals, that integrates to infinity. So you can't. So basically, like, you cannot. I mean, it's a good exercise to do. Like, try and construct P and Q whose characteristic functions differ only on these individual points in the Fourier domain. And the way that I thought about it earlier, like originally, is how you thought about it. Like, what if I added a cosine? Okay, I can't do a cosine. What if I had a cosine that decayed? Like, and so on and so on. But then we realized actually that characteristic functions are uniformly continuous, which is to say that actually, like, they can't just have a little difference that jumps only at a single point anyway. And so that sort of ended our debate, yeah. So this gives us our main theorem, which is that if I have a kernel on RD, how do I tell if it's characteristic? I take its Fourier transform. If the Fourier transform is not 0 on an interval, I can't find two distributions that differ, which this will not see. So basically, it's characteristic. So take Fourier transform, check if it's 0 on an interval. If it's not, it's characteristic. It's allowed to be 0 at points, but just not over an interval. This is something which at least is a little bit amazing. So if I have a kernel which is continuous and compactly supported, so an example is this kernel here, the witch's hat kernel, which is like flat, then a triangle. Okay? This kernel here, or indeed any kernel which is continuous and has a compact support, is characteristic. And the way to think about it is that these kernels with compact support end up looking a bit like this green function here, which is 0 only on points, but not on an interval. So that's the intuition you should have for that. But this is, I don't know, to me this is quite a surprising result, because a kernel with compact support, like, it doesn't even see the whole domain, it only sees locally. But that's enough to tell distributions apart. So are there questions about this characteristic property, or is that clear? Okay, so I want this to be non-mysterious. And it is very easy to check for translation invariant kernels. Okay, I'm going to skip over that because that's just restating what I just said. One clever thing is that using this same argument, you can find whether kernels on much more exotic domains are characteristic or not. Basically, whenever you have something that acts a little bit like a Fourier transform, you can use the same argument. So it turns out, periodic domains we've already seen, you have a Fourier series, so you can make this kind of argument and figure out whether it's characteristic or not. But then things like orthogonal matrices, like if you have a distribution over robot configurations, you might want to say, like, is this distribution over configurations the same as another? And you can do that as well, because something like the Fourier transform applies to sets of orthogonal matrices. And if you have a distribution over histograms, so that's like a distribution over distributions, you can make a similar argument. And you can say, like, is one distribution over histograms different to another? So, like, images might be a good application. Images that are represented as histograms, for example. Just as another quick note, you don't need to just use the difference in feature means to compare your distributions. You can use something like a Fisher statistic, which is a difference in feature means normalized by a feature covariance. That also works. And there's a family of distances called energy distances, which are quite popular in statistics. These are also a special case of kernel distances, and maybe if I get time, I can show why that is. Okay. So I promised I would now talk a little bit about how to determine if a distance was significant or not. Okay, I've defined my distances. I know the family of distances which will always distinguish distributions. Now I have sets of points from P and Q. I want to tell whether the difference between points from P and Q is large enough to be unlikely to be due to chance. Okay, so that's hypothesis testing. So here's one of the examples I started my talk with, right? I've got these waveforms, which are of length 100, recorded in the brain. These ones are recorded in the presence of a spike burst. These are recorded in the absence of a spike burst. I want to tell whether the distribution over these waveforms is significantly different to the distribution over those waveforms. This is my goal. Yeah?
Can you say how the spike burst was deleted first, because it's kind of a...
Yeah, so I mean, we like low-pass filter like crazy, right? Because these things are quite low frequency. Like spike is way above the frequencies at which we filtered for that. Yeah, because this is local field potential. So these are like, the cutoff is something like 20 hertz or something. So, or I would have to look that up. I will figure out the correct answer for that.
By the way, we need IID assumption, and
Here, I think the IID assumption is fine for these, because like these are over repeats of an experiment. So I didn't take a long time series and then split it into chunks. These are all like separated in time. So IID is fine here.
you mean the IID between chunks?
Exactly. So this in each of these waveforms is independent of another waveform.
So you take this as a separate vector?
Exactly. So my samples is, yeah, so that's actually a good point. So each sample is an entire waveform from 0 to 100. So I'm not just saying like, point 1 is sample 1, point 2 is sample 2. Each sample is a waveform. I have many, many such waveforms, and I'm comparing waveforms. So that's an important distinction. Yeah. So here are the waveforms that I get in the presence of a spike burst. Here are the waveforms I get in the absence of a spike burst. Okay. And actually, I'll skip over this because we already went over it. Okay, so now let's say that I'm just going to, well, first of all, define a little bit of terminology from hypothesis testing. So what I have on one hand is a null hypothesis that P and Q are the same. Okay, and this is my default, and I only reject it if I have enough evidence to conclude that they might not be the same. Okay? And H1 is my alternative hypothesis. Okay? So I've computed a distance between P and Q, and now on the basis of that distance, I want to decide whether to accept or reject the null hypothesis. So basically, like, is this distance pretty small, and is it unlikely that P and Q are different? Or, is it likely that P and Q are the same, or is this distance really huge, so it's very unlikely that P and Q are the same? That's what I want to determine, okay? So for this, I need a threshold, like what is small and what is large, because, at some point I have to make a decision. And so one way of arriving at that is to basically, like, imagine if I had many, many repeats of my experiment. So, like, if I generated many, many instances of a distance between P and Q, what would it look like if P and Q were the same? Okay? Like, what kinds of distances would I get if P and Q were the same? And that gives me an idea of the kind of behavior I would expect if P and Q are the same. Then I look at my experimental distance relative to that reference set of samples, and if it's way bigger, then it's okay, like P and Q are probably not the same. So that's my sort of reasoning here. Okay, so here is my distance between P and Q. So I've got the average similarity between points of P, average similarity between points of Q, and then average similarity between samples from P and samples from Q. Okay? So let's say that P and Q are different. If I repeated my experiment many times, so I've got my samples from P and Q, I compute the distance, I repeat it, then what would my histogram of distances look like? Well, it would be distributed according to a Gaussian distribution whose mean was the population distance, like the infinite sample limit distance of P and Q, and whose variance is this expression here, which is a function of the kernels. Okay? So let's see what that looks like. So here are P and Q, and you can see they're different. They're two Laplace distributions with different variance. I generate samples from P and Q, I compute the distance, and I repeat it, like several hundred times. And then I get the histogram of distances. So this histogram has a mean which is not 0 because P and Q are different, and it has some variance. So I don't get exactly 0 because I've only got finite samples from P and Q, but I get something scattered around the mean. Yep? Okay. So this is the kind of behavior I expect my distances to have if P and Q are different. What if P and Q are the same? Well, then actually things get quite unpleasant. So this is the distribution of the expected distances between samples from P and Q when P and Q are the same. And you'll notice that it's an infinite sum. It's an infinite sum of chi-squared random variables with weights which are the eigenvalues of my kernel with respect to the unknown P. So this is looking quite nasty, and that's deliberate. It's to give an idea that this might be quite hard to compute. Okay, why is it hard to compute? Well, first of all, because it's an infinite sum of independent variables, and the weights of these sum are the functions of eigenvalues with respect to a distribution I don't even know. So this looks pretty helpless, okay? Because I want to get a sense of how my distance between P and Q might be when P and Q are the same, but now I've just run into this rather unpleasant equation. So let's see what this looks like in practice. So I've just, so in this case, P and Q are the same and P and Q are Gaussian in this example here, okay? And this is the distribution of my distances between P and Q when they're both the same Gaussian. So I repeat the experiment many, many times. And I get this histogram here. And you can see it looks nothing like a Gaussian. Okay? And this is kind of unfortunate because what I really want to have is a threshold here, and I want to be able to say, well, if my distance, if my MMD was above this threshold, then it's very unlikely to have been generated by P and Q being the same, because this is the kind of typical behavior I need when P and Q are the same, but my distance was way out here. So that's very unlikely. But the bad news is that I can draw this on MATLAB, but how do I compute it? So I can tell you. So here is just to give you the intuition for this. Okay, here's my distance. This is my null distribution. So this is the distribution of distances I would expect if P and Q were the same. This is the threshold that I want. So basically, I want to say, like, with some small probability alpha, if P and Q are the same, I would exceed this threshold, but it should be very small. So I should say, like, exceeding this threshold is very unlikely when P and Q are the same. Now, if P and Q are different, let's say that they're different and their mean is here, I miss seeing this difference if I'm unlucky and if my statistic ends up in this part. So this is the kind of distribution of typical statistics I would imagine seeing when P and Q are different. And sometimes I'm going to make a mistake. And sometimes I'm going to say, well, I believe that P and Q are the same because I've got a very small distance, but actually I was unlucky and really they're different. So is this figure clear to everybody, or are there questions about it? Yep?
Why is the x-axis go below 0 when it's n times
That is a
squared?
very good question. So this seems a bit weird, right? Because I've computed an estimate of a squared distance between P and Q, and yet my density for both the null and the alternative allows negative numbers. That seems a little odd. Now, the reason it isn't odd is because this estimate here is an unbiased estimate of a squared distance, right? So that means that, like, unbiased means that in expectation, if I have this empirical statistic, I take the expectation over P and Q, I will get exactly the infinite sample value, okay? So that means that my distance needs to have mean equal to the population value, okay? So now, let's say I'm in the null case. The population value has mean 0, okay? So I've got a random variable. I draw lots of random samples, and I need something with a mean of 0. So that means that I need to have my samples scattered both above and below 0 for that to be true. Alternatively, I could add a bias to push this up above 0, like to push that up so it would always be non-negative. And this might be a good idea to do, because I might say, like, I want a squared distance. I don't want my squared distance ever to be negative. So even for finite samples, I want it always to be positive. And so I add a little bit here. So then I would have a non-negative but biased distance rather than an unbiased but sometimes negative distance. Yep? Okay. So how do I've just said that this is horrible. How do I get it? So one way to get an estimate of this thing here is to use something I'm going to call a permutation approach, okay? Because this is probably, apart from computational costs, the most practical way of doing this. Don't worry about this plot. So basically, what's the idea of a permutation approach? I've got samples from P and Q. I throw them all into a bag together. I take half of them out. I say, okay, this half is P. I take the other half out. I say, that half is Q. And then I compute the distance. Then I throw everything into a bag again, and I repeat it. And if I do that many, many times, I would expect to see something that looks like the distribution of MMDs I would get if my distribution were like a mixture of P and Q, right? So like, I have a sort of new pseudo-distribution for P, which I'll call P tilde, and a pseudo-distribution for Q, which I'll call Q tilde. And P tilde and Q tilde are exactly the same. They're both mixtures of P and Q. So that's the idea. Yep? Okay, so to show you that idea now in very simple math, here is my original statistic, right? So this matrix here is the matrix of kernel values between my pairs of samples from P. This matrix here is my matrix of kernel values from my samples from Q. And these are the kernel values between samples from P and samples from Q, okay? So remember what I did. I took the average of these two matrices, and I subtracted off the average of those two matrices. Or, in shorter notation, I took this W vector, which has 1s in the first n entries and minus 1s in the second n entries. I took the outer product of these, so I get a block matrix with like 1s in the top and bottom diagonal, and minus 1s in the other diagonal, and then I entry-wise multiply these together and sum all the entries. So I get pluses here and here. I get minuses here and here. I sum all the entries. I get the average distances here minus the average distances there. Okay? What does permutation do? It just scrambles up the entries of this. Okay? So I just like take my 1 minus 1 numbers, and then I just randomly permute them. And then I do this same thing here. Yep? Oh yeah, good. Okay, so visually you can see what this means, right? Like let's say that P is, let's say P and Q are different, okay? So P is more similar to itself, and Q is more similar to itself than P is to Q, right? But now if I multiply by this matrix which has minus 1s and 1s like flipped all over the place, then I get something which looks pretty much uniform. So if I take the average of all of the entries in this matrix, it will come to something pretty close to 0. And that's what I'm doing when I take this sum here. So is that clear? Okay. So now let's see how well it works. And this is an experiment I just coded up on MATLAB for the case of the two Gaussians with, which were identical. This red curve here is my infinite sum of chi-squareds. So the weights decay fast enough that I can just take a sum over a finite number, and it's enough to get a pretty good plot. The histogram is what I get from this permutation approach. And you can see they're a pretty good match. So if I do this permutation approach, and I take a threshold that I've obtained with this histogram, then I'm getting a pretty good test. Mm-hmm.
Does this approach approximate the asymptotic or the finite sample distribution?
So this approach will converge to the correct asymptotic distribution. This permutation approach.
Finite sample one.
Right. So the question of how well it works for finite samples, I'm not sure of that. So I think Larry Wasserman was saying if you use permutation, that it is correct at finite samples. I have not read the math, so I cannot guarantee you that, but I will make an appeal to authority and say that he said it's true. Yeah. But as long as you have enough samples, hopefully you're in the right ballpark. Yeah. So here is my LFP signals, and so in this slide, I want to first draw attention to this plot. So this is type 2 error. So this is the probability of incorrectly saying that the LFP samples are the same with and without a spike burst, okay? So you don't want to make that error, so smaller is better. And on this axis here, you see the number of traces, the number of these little time series that I've seen from P and Q. And what you can see here, this dashed line is permutation. This error is dropping as I see more and more samples from P and Q. And as by the time I've seen about 300 samples from each of P and Q, I'm making something like 4%, 3% error. So I'm pretty certain that I'm able to distinguish the distribution of LFP signals when I've seen a spike burst and when I haven't. So this is pretty nice. What I've plotted along this is sort of an advertisement for another approach to the problem, which is I've got this infinite weighted sum of chi-squareds, but I might choose to replace these weights by something I could compute empirically, which are the eigenvalues of my kernel matrix. So there's only finitely many of them, so that might seem a little bit off. But what you can show is that even if you do that, this sum here will converge to the right distribution as you see more and more samples. And so this red line is the error that I get when I use that approach. And depending on the size of your matrix, that might end up being faster than this permutation approach. Okay, so I think probably, now's a good time to stop. So are there any questions about this part? Yep.
How does the choice of kernel affect the ability to distinguish between the two?
Okay, so kernel choice is a very good question. So I will give you just quickly an intuition. If you use too broad a kernel, your function's too smooth. So basically, P and Q will always look the same, and you won't see a difference.
So the same intuition as an
Yeah.
classification?
So yeah, but if you choose too narrow a kernel, you might think, well, now I'm really sensitive to differences in P and Q. The trouble is, remember that bounded continuous function example, I won't be able to tell when a difference is meaningful, because even if there's no difference, the distance I'll see will look the same, because my kernel's so skinny. So like, unless my points hit exactly the same location, I'll think that everything is an instance when P and Q are different. So, you know, when I do my permutation approach to get my null, the kind of statistics I'll see will be exactly the same as the statistic I'll see when P and Q are different. So, you know, I'll be very sensitive to everything, so then nothing matters anymore. So what I want to do is to find some balance between choosing too broad a kernel and choosing too skinny a kernel. Hopefully in the next lecture, I'll tell you how to get that balance. Yeah, so I have a set of slides for that. Are there any further questions? Okay, so thank you.